Okay. So we are proving, this is a proof of the Archimedean property, and here's a statement of it. If you have two positive numbers, a and b, then for some positive integer n, we have n times a is bigger than b. Okay? So a and b bigger than 0 implies there exists a positive integer n such that n times a is greater than b. Now we're just doing a picture just to explain the idea. And this really goes to n being unbounded. So a and b are positive numbers, so we can put them ahead of 0 or to the right of 0. And of course, if you have a, you can put in the integer multiples of a, 2a, 3a, 4a, 5a, etc. And the point of this theorem, the point of this theorem is to say that you can always find a positive integer big enough so that that integer multiple of a is greater than b. Okay, so let's go ahead. I kind of jumped ahead. So we're going to do the proof by contradiction. Suppose not. Then there's an a and a b. This shouldn't be a and b and r. Oh, yeah. No, we're fine here. Such that a and b are positive. And for every positive integer n times a is less than or equal to b. So we're doing a proof by contradiction. So let S be the set of these multiple integers of a, positive multiple integers of a. This is a set that is clearly bounded above by b. It's also a set that is non-empty because a belongs to our set S. So it's non-empty, bounded above, and by the completeness axiom, there exists a supremum of this set. There's also a subset of R that's by construction. So there we go. So this statement here gives us the fact that S is bounded above by B. That's how we defined S. So we can invoke the completeness axiom. Say we have a supremum S naught. That's an R. It's going to be the supremum of our set S. And it's going to be an element of R.
It's 1 o'clock.
Thank you.
It's 13 hours.
Thank you. So S naught minus A is not an upper bound for our set S. Why not? Because if S naught is the least upper bound, then anything smaller than S naught is not an upper bound, right? So since S naught minus A is not an upper bound, there's a point in S that is bigger than S naught minus A. So say that's N naught times A. But now we can rearrange to get that S naught is less than 1 plus N naught times A. And this is a contradiction to the fact that S naught is an upper bound of S, right? Because 1 plus N naught times A belongs to S. And so there are two properties or two facts that flow or that are an easy result of this Archimedean property. So I kind of want to mention those. And so we can consider these corollaries. So the first one is that if you have a positive number, then there's a positive integer whose reciprocal is less than that number. So in particular, this is one way to show that there's not a smallest number. There's not a smallest positive number. Okay. And the second corollary is kind of similar, but instead of finding smaller numbers, we're saying that you can always find an integer that's larger than any number. Let me rephrase that. For any number, you can always find an integer larger than that particular number. You can't find a number that's an integer that's bigger than all numbers. So here we go. So if A is positive, and even if A is negative or 0, then there's a positive number, positive integer n that is greater than A. Okay. And in fact, we use this second fact in the proof of the density of the rationals. All right, that's it.